Hello everybody, good morning. We are Antonio Hernandez Monsalvo and Sebastián Aguilar Paz, and we are going to talk about arrangement of capacitors in series and parallel. This is the practice number 5. Let's start. First we have to find out the objective, which is to determine the individual charge of capacitors with different capacitance in order to calculate the equivalent capacitance for different circuits. Now we're going to pass to the introduction, and we're going to learn some important terms that we're going to be using during this practice. First, we have to understand what is a capacitor. A capacitor is a device in which electric charge and energy can be stored. They normally consist of two conductive objects that are placed very nearly, but they never touch each other. Capacitors usually consist of two plates of area A that are separated a distance d. When we are drawing a diagram, we can represent a capacitor in this way or in this way. Both are correct. Another term we have to remember is capacitance. The capacitance is the ability of a device to store the electric charge. The SI units of capacitance are farads. Capacitance depend on 5 factors: geometry and materials of the capacitor, size, shape, relative position of the two conductors, materials that separate the plates, and the geometry of the materials. To find out the capacitance, we have the following formula, which is Q equal C times V, which Q is the charge, V is the voltage, and C is the capacitance. Let's remember that the capacitance is in farads. The charge must be measured in coulombs and the voltage in volts. In this practice, we use a new element, which is the protoboard. A protoboard is a plate where you can do proofs. It is made to insert electronic elements and cables in order to form a circuit. Protoboards have little holes that are connected between them. The protoboard have to be connected to a battery with a positive and a negative terminal. In the upper and the lower parts of the board, we have connection strips, and all the holes are connected to the same strip. Another important concept we have to understand is loop. So a loop is any closed path in a circuit that does not have the same node more than once. So it begins with a starting node, and then we return to the same starting node without passing any other more than once. So we can say that a capacitor is connected in parallel when the terminal of the capacitor shares terminal with the battery, and when all the capacitors are connected to the same terminal. When we have a parallel arrangement in parallel, we can reduce it into a smaller capacitor. This is called equivalent capacitance. So if we are analyzing a circuit in parallel with the capacitors connected in parallel, we have to start with the formula Q equals C times V, which is the formula I have already showed. We have to take into account that the charge is distributed among the capacitors and the voltage is the same for all capacitors. So when we start with this formula and we want to find the net charge, we have to add the charges of the individual capacitors. So we have charge 1, which is Q1, which is C1 times V. We have charge 2, which is C2 times V. We have charge 3, which is C3 times V, and the charge N we want. So if we want the total charge, we can express it like Q equal Q1 plus Q2 plus Q3. So we just have to add them. And then we can write them again differently, which is Q equals C1 plus C2 plus C3, and all these terms multiplied by V. And if we want the equivalent capacitance, we only have to use the formula C equivalent is equal to C1 plus C2 plus C3 plus the Cns we want. Now we're going to analyze the arrangement in series, which is when we have a capacitor one after another, and the upper plate is connected to the positive terminal, and the lower plate of the last capacitor is connected to the negative terminal. So now we're going to analyze the capacitors connected in series. So we start again with the same formula, Q equals C times V, and we look that the voltage is going to be distributed among the capacitors, so Q is going to be constant. So Q is equal to C1 B1, Q is equal to C2 B2, and Q is equal to C3 B3, and so on. Now we can add all voltages. B source is going to be equal to the voltage of each capacitor, which is B1 plus B2 plus B3. Now, if we have the C equivalent, we have to do Q over C equivalent, which is equal to Q over C1 plus Q over C2 plus Q over C3. And we can rewrite that like 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3. So we can say that the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and all of these terms to the minus 1. The equipment we use in this practice was an app, which is the Circuit Construction Kit, which is the following: the PHET Interactive Simulations. Inside the app, we use some equipment, which is a voltmeter, a wire, a battery, and some resistors, and also a switch. We're going to discuss the procedures. To carry out this experiment, we use a specialized software which helped us to simulate the electrical circuit. First, we set the different capacitance value for each of the capacitors used in each arrangement. For the parallel and the series arrangement, we use three different capacitance, which were 0.15 farads, 0.12 farads, and 0.08 farads. While for the complex circuit, we used the following capacitance: 0.16 farads, 0.13 farads, 0.11 farads, and 0.08 farads for each capacitor. The voltage in the battery that we used were 10 volts. So these were all the data. And now we start with the first configuration, which is a parallel arrangement in which is supposed to have the same quantity of voltage in each capacitor. The second one, a series arrangement, where the capacitor is placed one after another and the voltage tends to be different in each one. The third arrangement was a complex circuit, where we had 3 parallel capacitors and 2 series capacitors. All the configurations I already mentioned, we use a multimeter to measure the potential difference values to compare them with the theoretical voltage for each capacitor. And finally, using the measured values of capacitance and voltage, the charges for the individual capacitors were calculated, and we determined the equivalent capacitance.
Now we're going to analyze the results for this practice. For our first circuit, which is a parallel arrangement of 3 different capacitors connected to a 10 volts battery, we can see in the illustrations that the voltage remains constant for each capacitor. This means that the voltage is going to be the same in the whole circuit. and therefore the equivalent capacitance can be calculated as the sum of the three capacitances. And here, in this case, the equivalent capacitance is going to be 0.35 farads. The equation to calculate the charge for each capacitor is the capacitance multiplied by the voltage of the circuit. So the capacitance of the number 1 multiplied by the voltage of the circuit is going to give us 1.5 coulombs. The charge for the second capacitor is going to be 1.2 coulombs, and for the third one 0.8 coulombs. Now for our second circuit, it is a series arrangement. Here we can observe that the 10 volts of the power supply is going to be divided between the three capacitors, depending on its capacitance. The voltage for the first capacitor was registered in 3.455 volts, for the second one 3.03 volts, and for the last one 3.242 volts. As we can see, the closer the capacitor is to the positive pole of the battery, the higher is the voltage that is going to be measured. In this way, we can define the equivalent capacitance using the following formula. That is 1 divided by the capacitance number 1 plus the 1 divided by capacitance 2 and plus 1 divided by capacitance 3. All of this rise to the minus 1. In this case, the value is going to be 0.36 farads, almost the same as that in the parallel arrangement. And to calculate the charge for each capacitor, we're going to multiply the capacitance by the voltage measured for each capacitor. In this case, the charge for number 1 is going to be 0.49 coulombs, for capacitor 2 0.40 coulombs, and for capacitor 3 0.28 coulombs. And finally, our last circuit is a complex arrangement. Here we have two capacitors in a parallel arrangement, that is the number 3 and the number 4. From this, we can calculate its equivalent capacitance, adding the two capacitances, which is going to give us 0.19 farads. And the rest of the circuit is a series arrangement. Since it is a series arrangement, we can calculate it using the previous formula, but instead of taking into account the capacitance number 3, is going to be the addition of the capacitance 3 and 4. Since we substitute the values, the equivalent capacitance for this complex arrangement is going to be 0.52 farads. What can we conclude from here? As we can see, we use the same capacitors for the first two arrangements, and the equivalent capacitance is practically the same in both cases. The charge registered on each capacitor are directly dependent on the capacitance value. And in the parallel arrangement, the voltage is constant for all the circuit, while in the series arrangement, the total voltage is divided proportionally on the capacitance value for each capacitor. In the case of the complex circuit, we could break it down to make it simple and make the study more easy for us. Thank you very much, and that will be all. Here is our bibliography.